Hello, and welcome to another power electronics class. In the previous class, we started the DC to AC inverters, um, specifically the PWM inverters. And as I mentioned, usually the DC to AC converters are called inverters. I explained about some of their applications, for example, for controlling AC motors, UPS, HVDC, and renewable energy for solar and wind. We learned a little bit about the concepts of the inverters, different type of inverters, the voltage controlled and the current source inverters. And we went through different types like the half bridge and the full bridge inverters as well. Today, we're going to start with the distortion in inverters and harmonics, and how can we utilize filters to eliminate harmonics in the systems, and what are the effects of harmonics in the system. So VSI, as you know, we had variable voltage and variable source inverters. I explained the problems that the variable source may cause. One of the problems, as you remember, if the voltage drops in the input, the output voltage also drops as well. To mitigate that, to compensate for that, we need to have a fixed input source, a fixed DC voltage source. And sometimes our DC source is a battery, sometimes it's a solar panel, sometimes it may be a wind turbine. And as you know, the wind doesn't blow all the time, the sun doesn't shine, so the voltage is fluctuating. To be able to control that, we can use a two-phase system, meaning we can use a buck boost in the input and precisely control the output voltage of that DC, and then feed it with a filter or a DC link to an inverter. So first we're going to have a variable DC output, which is a buck boost converter, and then we would have the inverter itself. And the purpose of this chopper or these variable DC voltage is to be able to provide a fixed input voltage for the second stage. Okay, and the second stage converts that to a AC signal with a fixed frequency and voltage. So where do we control the voltage? At the first stage. Where do we control the frequency? At the second stage. Now, in these systems, we may have a problem, but most certainly we have. And sometimes the harmonics is going to be a problem. Sometimes we don't care about them that much. Depends on what application do we want to use these AC signals. So for a VSI with a fixed DC link, the DC voltage is held constant. Again, the reason is because we want to have a constant amplitude at the output AC signal. And the output voltage and frequency are varied simultaneously using the PWM techniques. By controlling the PWM at the first stage, we can control the voltage. Again, because it's a buck boost converter, and it's a variable DC converter. And by controlling the pulse width at the second stage, we can control the frequency as well. And this shows an inverter with a fixed DC link. And one application for this is going to be EVs, because then an EV usually needs to have control over the frequency. If the EV is using a synchronous AC for an AC motor, we can control the speed of the motor, therefore the wheel and so on, by controlling the frequency, and controlling frequency is through controlling the PWM. Now, harmonics in a square wave inverter The output voltage of an inverter is rectilinear in nature and therefore contains harmonics. The problem with the harmonics is that, first of all, harmonics have effect on the power quality, on the output quality, and therefore they would have the effect on the efficiency. And sometimes they have adverse effects on the load as well, as mentioned, because they are abruptly changing from positive to negative and negative to positive. It creates sparks. If you have an AC motor, it's going to, in long term, initially it may work, in long term it's going to damage the motor. And harmonic reduction can be achieved with filtering and or using the harmonic elimination techniques, which I'll explain. So for example, if we have an induction machine, an induction motor, the harmonic can affect it in 3 different sequences, and it will affect the stable operation of the motor. We have the 1st, 7th, 13th harmonic, which produce a positive VE sequence, or the ABC. The 5th, 11th, and 17th produce the negative VE sequence. The triple harmonic 3, 9, 15 produce 0 sequence, and the harmonics cause distortion on the output voltage. And the lower harmonics are usually more difficult to eliminate because, first of all, those have a closer frequency to the fundamental frequency, and they have the highest amplitude. Therefore, you need a very large capacitor, inductor, and the filter order must be higher, meaning you need a 2nd order, 3rd order. So you need the RLCs for, you can't just filter out with a normal capacitor. And they can cause, because their amplitude is higher, frequency is closer to the fundamental frequency, they could cause serious voltage distortion. Sometimes we just filter out the 3rd, 5th, and 7th harmonics, and after that it's so little, and I'll show you an example and a picture of how they affect the system, that we usually don't care about the rest. So why do we need to consider harmonics and eliminate them? First, if you have this question on your exam, it's about power quality. We want to increase efficiency, and the harmonics is technically a waste of energy in the output. And the harmonics may cause degradation of equipment, and equipment need to be derated. Again, if we want to use this in electronics, it's not going to cause a problem, but if you want to run this to turn any type of motor, it's going to cause problems. Now, this shows, this is a very interesting graph. The upper graph shows the output voltage in a square wave inverter. So normal inverter, square wave looks like this, the output. And the second one shows the fundamental component, which you can see has the same frequency, same amplitude, but it has a sinusoid output. And technically what we have is that square inverter, you can extract all these signals from it. If you remember from signals and systems, how many of you have passed signals and systems? And you had Fourier transform. You remember that a Fourier transform is basically you can extract all the components of the frequency components of a signal using Fourier transform. What does that mean? It means if I combine the 3rd, 5th, and so on, all the harmonics with the fundamental, I will create the original signal in the output. So these are basically the building blocks of that square signal. But the thing is, the thing that we are interested in is just the fundamental component, which is the sinusoid signal. Okay, the rest of the harmonics, they are going to cause problem. They're going to reduce efficiency, and they are gonna create what we call a knocking effect in the motor and creates degradation. So that's the first harmonic. Then we have the third harmonic, which is 3 times the frequency of the first. And we have the fifth harmonic, which is 5 times the frequency of the first harmonic. And if you, again, combine all of these harmonics, you're going to create the original square signal. Here we only have shown the odd harmonics. We don't show the even harmonics because the even harmonics are going to zero out. They're going to have no effects. Even ones are going to cancel out, and they would have a sum of 0. So even harmonics don't cause problem. Only the odd harmonics do. And the lower the number of harmonics is, it's going to create a bigger problem. Meaning the third harmonic is more dangerous than the fifth, than the seventh, than the next. So fifth harmonic is going to have a huger impact compared to the seventh harmonic or the ninth or so on. And the other thing is, the higher the number of the harmonic is, it's going to have a smaller amplitude or a smaller magnitude. Okay, so the fundamental harmonic has the amplitude of V1, and this is very important as well. So original signal, VDC. The fundamental harmonic or component is V1. The third harmonic is V1 divided by 3, so 1/3 of that. And the fifth harmonic is V1 divided by 5. So the seventh harmonic is going to be V1 divided by 7th. The ninth one is going to be V1 divided by 9. Okay. The seventh one is going to have a frequency that is 7 times, so it's going to look like this. And the ninth harmonic, so the higher the harmonic is, you're going to have a higher frequency but lower amplitude. I forgot to. Let me show it like this. So the seventh harmonic is going to look like this black one. This is going to be the seventh. And the amplitude would be V1 over 7. Okay. Again, when we write the Fourier transform for the Fourier series transform for the square signal, we're going to get all these harmonics. The one that we are interested in, we want a pure sine wave, so the first or fundamental. And again, I'm not going to go through the signals because that's a topic of another, and the harmonic, the Fourier transform, the Fourier expansion, that's a topic for signals and systems. But you have the fundamental, third, fifth. We are interested in the fundamental. The rest of it must be filtered out. Now, how can we filter this out? Using an RLC filter, but that causes a problem, and I would explain what problems and hurdles do we have. So total harmonic distortion, or THD, is the measure to determine the quality of a given waveform. So in an exam, if I ask, or if we have a question that what determines and how do we measure the quality of the waveform, we do it by measuring or calculating the total harmonic distortion, or THD. Now, we can measure the total harmonic distortion for the voltage, or we can measure it for the current. So we can do it for both the voltage and for the current. If the voltage is fixed, we could do it for the current as well. So if we have a fixed DC system, a VSI, and we can find the current as well. And the equation goes as follows. Vn is the nth harmonic voltage. Therefore, total harmonic distortion for the voltage is going to be equal to square root of the sigma from 2 to infinite, Vn RMS square over V1 RMS. Why did we start n from 2? Why didn't we start n from 0 or 1? Why didn't we start from 1? Because the first harmonic is the fundamental harmonic, and we want to keep that. And we divide it by the V1 RMS, which is the fundamental voltage. As you can see here, it's our fundamental voltage amplitude, V1, okay? So that's the reason we start from do. We want to start from the third harmonic technique. So this would be equal to square root of V2 RMS square plus V3 RMS square plus V infinite RMS square over V1 RMS. And n equal to 1, as you know, is the fundamental voltage. As mentioned, the even harmonics usually don't have an effect. We are interested in the odd harmonics, the third, fifth, and we don't necessarily want to go to infinite. After the seventh or ninth harmonic, we usually say, okay, 7 harmonic is enough. The effect of that harmonic is going to be so minimal that it's technically not going to create distortion or any problem. Okay. Now, if the RMS voltage for the waveform is known, again, if we have a fixed voltage link, then we can find the total harmonic distortion for the current. And for that, THD I is going to be equal to square root of sigma IN via RMS square from n from 2 to infinity over I1 RMS. And in this case, using Ohm's law, IN is going to be Vn over Zn over the impedance, and the Zn is the impedance at the harmonic frequency. Now, the first way to eliminate the harmonics is obviously when you have unwanted frequencies and signals. First line to eliminate it, first thing is going to be using filters. So as we know, we use harmonic filtering. As we know, the output of the inverter is chopped AC voltage with 0 DC component, and it contains harmonics. An LC section low pass filter is normally fitted at the inverter output to reduce the high frequency harmonics. In some applications, such as UPS, a high purity sine wave output is required. So good filtering is a must. In some applications, such as AC motor drive, filtering is not required. So the motor drive itself. Example, if you want to convert that back to a DC, you want to run a heater or any electronic device, you don't need the filter. And because we have this filter, it actually makes these pure sine wave inverters very expensive. And there are other ways instead of filters as well to be able to reduce harmonics, and I'll explain that one as well. So the way that the whole system works for a sine wave inverter is that we have a DC supply. It could be the battery of your car. Then we have a fixed DC, or what we call a link, or what we call a variable DC system connected to an inverter. And again, these two have a fixed DC link together. That's exactly what we saw here. Let me go back a little bit. It's exactly this one. So we can draw this one like this. We have a DC and an AC. DC to DC chopper and an AC system. And the output of that is connected, the output of the inverter is connected to a low pass filter, an LC. Again, if we want to reduce all the harmonics, we need a higher order LC, meaning we need 2, 3 inductor capacitor systems, so second order, third order, and so on. So before filtering, we would have a square signal, and after the filtering, we're going to have a somewhat close to a sine wave signal, and then that's connected to the load. Now for the filter itself and how to compute that, we need to find the harmonics and the Fourier series for that. So study of harmonics requires understanding of wave shapes. Fourier series is a tool to analyze wave shapes. So the harmonics of a square wave, we have A0 is going to be equal to 0. An is going to be VDC over pi. Integral of 0 to pi cosine of n theta d theta minus the integral for pi to 2 pi cosine of n theta d theta, which is going to be equal to 0. And Bn, which is going to be VDC over pi. As you know, for the Fourier series, we have the integral of cosine plus sine. So the cosine part is going to be 0. The sine part is the one that we have some value. And by solving that part, VBN, we finally get to this. It's going to be 2 VDC over n pi, 1 minus cosine of n pi. So when n is even, cosine of n pi would be equal to 1, and Bn would be equal to 0. So therefore, even harmonics do not exist. This is very important, okay? This is very, very important. So when n is odd, cosine of n pi is going to be equal to -1. Therefore, Bn would be 4 VDC over n pi. This is the peak value of the fundamental sine wave. To obtain the RMS value, simply divide the peak value with square root of 2. So again, this is the peak value, VBN, let's say peak, if you want to find that. So is it clear? Yes? Okay. Now, for example, if we want to find Bn for, let's solve a quick example. So we want to find a Bn. VDC is equal to 12 volts. We want to find it at its third harmonic and first harmonic. And yeah, what is Bn equal to? Bn is, by the way, the peak fundamental sine wave. If we want to find it at peak, it's n is going to be equal to 1. But we want to find it at third one as well, at third harmonics. So what is it for the fundamental? Yes, it's going to n is going to be 1. Yes. 15.28. 15.28. And if I want to find the RMS value, it's going to be 15.28 divided by square root of 2. Okay. And what is it for the third? Yes, we would just divide this by 3. If you divide this by 3, because you know it's V1 divided by 3, it's going to be 5 point what? 09. Yeah. And this is going to be for VB or BN3. 5. For the fifth one, it's going to be that divided by 5. Okay. Now, the spectra of square wave, the spectra or the harmonic characteristics is that the harmonic decreases with a factor of 1 over n. Okay, these are very important. Even harmonics are absent. We don't have any even harmonics. The nearest harmonics is the third. If fundamental is 50 hertz, then the nearest harmonic is 150 hertz, so 3 times the frequency, and 1/3 of the amplitude. Due to the small separation between the fundamental and harmonics, output low-pass filter design can be very difficult sometimes. This is a very good graph showing the fundamental, which is the first, third, fifth, seventh, ninth, and 11th. And you can see that the higher the harmonics is, the amplitude drops, the frequency goes up. So the third harmonic is 1/3 of the original. The fifth harmonic is 1/5, and for seventh harmonic is 1/7, and so on. And the frequency for the third harmonic is 3 times the fundamental frequency. I'm going to call it F1. So this is 3 times, this is 5 times, this is 7 times, and so on. So you can see that the higher the harmonics go, the effects become less and less. So after, usually the rest has minimal effect. It's negligible, okay? 9th or 11th, depending on how good your output signal want it to be. If you want to be very pure, accurate, you want to use a medical device, 11 harmonic. But the good thing is, when we filter, for example, this after the third harmonic, all of these are going to be eliminated, okay? Now, how can we eliminate the harmonics? Imagine this is the frequency response of the system, and we want to just pass the fundamental, we want to eliminate everything else. What type of filter do we need? Do we need a low pass filter, high pass filter, or a notch filter, band pass filter? So I want to go back to this picture. Which one do you want to keep? We want to keep the fundamental. So we want to eliminate the third harmonic and the fifth harmonic. Am I correct? Yes. So the third harmonic and the fifth harmonic, do they have a higher frequency or a lower frequency than the fundamental frequency? Higher frequency, okay? So in order to keep that fundamental component and filter the higher ones, what type of filter do we need? We want to keep the low frequency, and we want to block or stop the high frequency. Therefore, we're going to need a low pass filter, okay? We want to filter anything that is below or close to F1, which is our fundamental frequency, and everything over that, and as you remember, this is pass band from signals and systems, and anything above that, it's stop band, okay? So we want to use a low pass filter, meaning a filter that passes the lower frequency and blocks the higher frequency. So if I can have a low pass filter and block anything that is above, let's say 100 hertz, then we can block the third, fifth, seventh, all the frequencies above 100 hertz. So imagine that our cutoff frequency here is 100 hertz, and this is like 150. So anything above 100 hertz is going to be blocked or stopped, okay? But the thing is, the fundamental frequency and the third harmonic are so close that designing this filter is going to be a difficult task, okay? Especially for high voltage. We can have a second order filter, but for high voltage, you need a very large capacitor, inductor. It's going to be expensive and challenging. And by the way, as you know, this is the frequency response. So this is frequency, and this is the amplitude, or let's call it A. So the quasi-square wave inverters, to reduce the harmonics order of the square wave inverter, or to get a variable RMS voltage of the inverter output, QSW can be used. The QSW status are shown below. So for S1, it's going to be 1100. S2 is going to be 0110. And this is for the different harmonics. And S3 is going to be 1001 and S4 is going to be 0011. And I'll explain more about this later as well. Now, thus the following output voltage can be obtained from the system. Again, this picture we got it from a. And note that AN is 0 due to half wave symmetry. And expanding that for BN would be cosine of n pi, cosine of n alpha, plus sine of n pi, sine of n alpha, which is going to be equal to cosine of n pi, cosine of n alpha. And you can see it. This is the system that we have. And the reason that we have these alphas is because we want to prevent short circuiting. And I already mentioned this in the previous class as well. And therefore, Bn would be 2V dc, and this is an important one. Going to be 2V dc n pi over n pi, cosine of n phi times 1 minus cosine of n pi. So if n is even, again, Bn would be 0. And if it is odd, therefore, and this is, Bn would be 4 dc, 4V dc over n pi cosine of n phi. In particular, the amplitude of the fundamental B1 would be 4 dc, 4V dc over pi cosine of phi. This is for this particular type of sinusoid. And as you can see, the previous one that we had a direct transition, a connection between the positive and negative. Here we would have a phi shift. Again, the reason is because we want to avoid that short circuit that we had in the bridges. So we would give it a small delay. So the fundamental B1 is controlled by varying alpha, and harmonics can be controlled by adjusting alpha. So now this gives us another idea. If we are able to delay this positive and negative part of the signal, therefore we can change alpha. Alpha has an effect on harmonic as well. So you can see that we can affect the harmonics by adjusting alpha. Now this gives us a good idea. So why don't we use this alpha and be able to control the width of the signal to be able to control the harmonic as well. So another way to control harmonics or eliminate harmonics is to control alpha. Okay, so one way is to use a filter, low pass filter. Low pass filter is going to be expensive. We still need that filter, but another way to do that is to control alpha. So for example, if alpha is 30 degrees, then B3 would be 0, or the third harmonic is eliminated from the waveform. In general, harmonic n will be eliminated if alpha is equal to 90 degrees over n. Okay, so if alpha is equal to 15 degrees, okay, no, let's say, no, just give me an, let's say, just give me 1 second. If alpha is 18 degrees, which harmonic would be eliminated? Let's say alpha equal to 18 and another one alpha equal to 8.18 degree. So which harmonics would be eliminated if alpha is equal to 18 degrees and 8.18 degrees? So n would be equal to 90 degrees over alpha. So for the first one, it's going to be 90 degrees over 18 degrees, which gives us 5. So if it's 18 degrees, then the fifth harmonic would be eliminated. But we will still have the third harmonic, okay? What about if it's 8.18? N is 90 degree over 8.18. It's going to be the 11th harmonic, okay? So what is the benefit of filters? When you apply filter, you eliminate all the harmonics after that, so the third, fifth, seventh, and so on. But when you control the alpha, you only eliminate one of the harmonics. So you can eliminate third, fifth, and so on, okay? So even if you use an alpha to eliminate the third harmonic, you would still need a filter to eliminate the seventh and fifth harmonic as well, okay? But the good thing about this is the most difficult harmonic to filter is the third harmonic with a filtering system. So you can eliminate with the alpha and the variable width, and then the rest of it you can use a smaller filter. Does it make sense? Yes? Is it clear? So the third harmonic, you can put alpha at 30 degrees. You would have the first, and you eliminated the third harmonic, and you can eliminate the rest using a filter. Okay, and now you need a filter that is 1/5 of the sides because it's don't need to pass a lot of voltage. The capacitor is going to be much smaller. The frequency difference is much higher, so you don't need a second degree filter. You need a first degree filter. So instead of 4 components, you would need 2 components, for example. Now let's solve an example. The bridge inverter has an RLC load, and this is from the book, with R equal to 10 ohms, L is 31.5 millihenry, and C is 112 microfarads. The inverter frequency is 60 hertz, and the DC input voltage is 220 volts. We want to express the instantaneous load current in Fourier series, calculate the RMS voltage, load current at fundamental frequency, I1, and harmonic factor of the load current, or HF, and the power absorbed by the load, PL, the average current of the DC supply, IS, and the RMS and peak current of each transistor. We want to draw the waveform of fundamental load current and show the conduction interval of transistors and diodes, and calculate the conduction time of the transistors and diodes. Again, this is a very complicated example, but covers everything. Now, the first thing that we need to do, we need to find the inductive reactance for the nth harmonic voltage. And for that, reactance XL would be 2n pi times the frequency times L, and L is in millihenry, so it's 10 to the power of negative 3. And that is going to be J 11.87. The capacitive reactance for the nth harmonic voltage is going to be the same thing. You have to find the reactance. So it's going to be 1 over pi. Where is C? Yes, it's 112 So it's going to be 1 over 2 pi fc, or for the nth harmonic, it's going to be 2n pi fc. And for that, it's going to be negative j 23.68 over m. And the impedance for the nth harmonic voltage is going to be Zn is going to be all the impedances of the diode, inductor, and also capacitor. The power factor angle for the nth harmonic voltage is going to be the tan inverse of the reactive over the real part, which is the inductor and the capacitor over the resistor. The instantaneous output voltage can be expressed as V out is going to be 280.1 sine of omega t plus 93.4 sine of 3, because it's the third harmonic, and then the fifth harmonic, seventh harmonic. So this is the fundamental, first, the third, the fifth, the seventh, the ninth, and so on. And dividing the output voltage by the load impedance and considering the appropriate delay due to the power factor angle, we can obtain the instantaneous load current as well. And only thing we have to do is we divide it by the impedance. And the RMS load current fundamental frequency I1 would be 18.1 divided by square root of 2, because we want to find the RMS value. It gives us 12.8. So we would divide this by square root of 2. And considering up to the ninth harmonic, again, after the ninth harmonic, it becomes negligible. The peak load current would be adding all them together, the first, third, so this is the first, third, fifth, seventh, and the ninth, gives us 18.41 amps. The harmonic factor of load current is going to be Im square minus Im1 square over square root of that over Im1, which gives us 18.59%. The RMS load current, I out, is going to be 18.41 divided by square root of 2, because again, we want to find the RMS. This is going to be 13.02 amps. And the load power would be multiplying that by 10, because we want to find the real power, and the resistor here that we had was 10 ohms. So it's going to be I square R is going to be 1,695 watts. The average supply current would be that power divided by the voltage. Again, this is I is P over V. And the voltage was 220 volts. This therefore gives us 7.7 amps. The peak transistor current would be the peak current that we had for the switch. The RMS current of each transistor would be that current divided by the square root of 2, or the peak divided by 2, which is 18.41 divided by 2 is 9.2. The waveform for the fundamental load current would look like this. So the output current is like this. You can see it's a distorted signal. You can see it over here when I'm following it. But the fundamental, which is what we are looking for, it's close to the sine wave that we have. And this is done with a simulating tool. Because again, finding all the harmonics is going to be difficult. So therefore, drawing the output is going to be somewhat challenging. And here you can see T on and D1 off, on, and T2 on and D2 on for the bridge switching system. Again, this example is just for you to be able to visualize and learn how to solve these problems. Obviously, in the exams, you're going to have something simpler than this. So another type of inverter that we have is going to be the three-phase. So far, what we studied was the single phase inverters. Now we have the 3-phase inverters. Here, each leg, and the red, green, blue refers to the second picture down here. The red, yellow, blue is delayed by 120 degrees, as you know, for 3-phase. A 3-phase inverter with the star connection load is shown here. You see, this is for a star connection. And the way that we can determine it's a star, you can see everything, the ground, it's the grounding of the 3-phase at the middle of the Y. We have two different modes for 3-phase inverters. We have the 180-degree conduction mode, and we have the 120-degree induction mode, and we would study both of them. In the 180-degree conduction mode, and you can see the pictures on the left and right, it's for the 180-degree and for the 120-degree induction mode. So 180-degree, if I'm correct, and this is 100. So in this mode, each switch conducts for 180 degrees. In each 60-degree state, 3 switches conducts together, either 2 positive switches and 1 negative, or 2 negative switches and 1 positive. So, for example, if T1, T5, and T6 conduct, then the equivalent circuit of the inverter can be derived as shown below. So the picture is a little misaligned. This is the picture for the 100 when the switches are connected. So as you can see, we have 2 of them, for example, in the positive conduction, 1 is in the negative. So T1, T5, and T6 are connected. If we draw the KVL for this, we can find the current coming from the source. So the current coming from the source is divided in 2 currents here and going back, combining here. And if I want to find the current, I can use a KVL or I can use Ohm's law, which is going to be this voltage Vs divided by the combination of these 3 resistors. These 2 resistors are in parallel, so RT for this part is going to be R plus times R over R plus R. In other words, it's going to be R divided by 2. And for the whole system, R is going to be R divided by 2 plus R. It's going to be 3 over 2 R. Now, if I want to find IS, I would divide Vs over the equivalent R, which gives us 2Vs over 3R. I think I had. So this is the way we get the source current. And in the picture, it's actually drawn better. So you can see that we combine these 2 R's. And by adding all the R's, we have the total R. And finally, we have IS. And we can find also each phase voltage, VAN, which is equal to VCN, which is going to be equal to Vs over 3. And VBN would be 2Vs over 3. So this is for each sequence when for this example was T1 and T5 are and T1, T5, and T6 are on. But we can do that and expand it for all the other switches. So the first one is, you can see T1, T2, T3, T4, T5, and T6. And the red one shows when the switches are on, and you can see when the switches are on or off, what happens in the output. So for each condition, you can see what the output VRN, VBN, would be for each of them. Let's start with the first one. So you can see that T5 is turned on, and then we have T6. And when both of them are turned on, you're going to have a step type of voltage. And then T5 is turned off, T6 is turned off, and then T2 is on as well. So you're going to have this last one. So this and this, these correlate, and when they correlate, they're going to create double the voltage, you can say, or yeah, 2/3 of the voltage extra from the original one. Here we have, yeah, and the same thing happens here, and then we have the negative voltage coming in. By the way, 2 of them are positive, 1 is negative, or 2 of them are negative, 1 is positive. And when you add 2 positive, no negative, you're going to have the maximum voltage. 2 positive, 1 negative is going to be half the voltage, for example, or 3 half of the voltage. And the negative is going to be opposite. So eventually what we want to create, we're going to create 3 different voltages because of how 120-degree phase shift that we have. And you can see that this looks pretty close to a sine wave signal for 3 phase. And each phase has a 120-degree phase shift between them. Okay. These, I don't know if I did it right, but these don't align perfectly. So the peaks. Okay. Now in this mode, the inverter switches states are as follows, this table. You can see that S1 is 111 means turns on, as 000 means turns off, turned off. S2 is 01110, S3 is 001110, S4 is 000111, S5 is 100011, and S6 is 110001. And you can see that it's turn on and half the time all of them and turn off at the other half. So that's the reason we call it 180 degrees. So it's on at 360 degrees, so 111, 60, 60, 60, and then 000, other 60s. So with our load, the diode across the transistor have no functions. If the load is inductive, the current in each arm of the inverter would be related to the voltage as shown in the following figure. So you can see that there is a small shift here because of the inductor between the voltage and also the current, which we showed with theta. So when T4 is off, the only path for the negative current, IR, is via D1. Hence, the load terminal R is connected to the DC source via D1 until the load current reverses its polarity at T equal to T1. During period of 0 between 0 and T1, T1 will not conduct. Similarly, T4 will only start to conduct at T2. The transistor must be continuously gated since the conduction time of the transistor and diode depends on the load power factor. I think it's enough to, oh, let me see if I can finish. I think it's enough up to here because 120-degree mode, that takes at least 20 minutes to complete with comparison between them. I want to speak a few minutes about your final project. The final project gives you an opportunity to compensate if you didn't do well in the exams. So you're going to have bonus points for that. For the final project, I want you to build a buck boost or a buck boost converter. And you don't need to build a variable system. Just use a simple op amp And a DC to DC converter, any type of DC to DC converter would work. If you build it using a PCB board, you're going to get extra bonus points. You can find you don't need to even design the circuit. You can find it online, a simple one. And but it's not required. And you can just build it using a breadboard. You just need a few components. And the final project I would recommend that you start, if you want to do that, work on it as soon as possible, because you need some parts that may not arrive, especially nowadays I see the parts are getting delayed. Yes, a physical buck boost converter using breadboard. And also if you want to get bonus points, you can design it using PCB and solder it. The other thing that I want to mention is about your second exam. When do you want to take your second exam? Do you mention 7 or second week of November? Yes. Are you all comfortable taking that exam? Okay. So we're going to have a review session, and we can set the exam right now actually. And just give me 1 second to bring the so we're going to have the week after next week, so probably 12. Is 12 okay with you? Okay. And I don't think we have classes on 26th, so the 24th, and then we have one class after that at 1st of December. So the deadline for the project would be December 1st. Okay. Have a month. If you want to, you can complete it in 2 days. The parts takes time to arrive. Okay. So the deadline is going to be December 1st. Second exam is going to be November 12th. The second exam is going to be again multiple choice, and it's going to be up to the 3-phase. So the exam is going to be up to the 3-phase inverters. So that 1 phase would be part of it, but 3-phase would not be part of it. The project, yes, you have to bring it in. So it's going to be on the last day of the last class. Okay. So yeah, for the online students, I will post a video on how they can do that. Okay. Do you have any questions for me about the project and the second exam? No? Okay. Thank you so much. And I would see you on Wednesday.